Okay, let's go to activity B2, saving data in efficient formats. This is all about step 4 of our pipeline. Act as the data management instructor, write a script that demonstrates the difference between saving research data as a plain text file versus a more efficient binary format. Script should generate a simulated data set with measurements from 100,000 time points across multiple recording channels. It should save the data set into a plain CSV file, so comma separated value file, and an optimized binary file such as NumPy's NPy format or HDF5. And then we want to compare the file sizes on the disk and measure how long it takes to load each file back into memory for analysis. Okay, so this is a subsection of step 4 for reporting the results, but it also can be thought in terms of its own pipeline because we also have our 4 steps represented here. So data acquisition, generation of the data set, data analysis, saving and comparison of the data size, and then step 3 and 4. Well, step 3 less so because we don't visualize anything, but step 4 we report, we compare and report the results and clearly state the trade-offs. Let's do this. You can see that the performance of the prompt window is starting to lag. So it's good that we're getting to the end of this notebook and we can restart the ChatGPT prompt window. Okay, so the code chunk is fairly small, which is good. So we are probably happy with it. It is executed. Okay, it runs. Let's quickly go over what it did. So it generated 100,000 time points recorded over 8 channels. And again, coming back to the exactness, we didn't specify how many channels we want. We just said across multiple recording channels. So this is the exactness point that we want to address. We want to specify the exact number of channels. Then it saves the CSV file. Then it saves the NumPy binary file, which is a more efficient file format because it compresses the data. This is the second exactness caveat because we are giving it an opportunity to save either as a NumPy format or as HDF5 format. It chose NumPy, but on reprompting it could choose HDF5 and the results would change. Then it compares the file sizes and it tracks how long it takes to load the CSV and the binary file into memory. So as you can see, the plain text CSV file takes 19 megabytes, while the NumPy file takes only 3 megabytes, super efficient, and well, it takes faster to load too. Well, here it doesn't matter that much because the file sizes are, well, small in absolute value. But when you deal with large data sets, especially with fMRI data sets, I keep going back to fMRI data sets, but this is really where most of these problems really come into place. It can take minutes to load a single data set or even a part of a single data set. So this saving becomes really important in these situations. And so you can see that here saving data in efficient formats well, provides a real time benefit in that regard, which is very important for step 4 on how we report results for reproducibility. Let us see now what we can improve. So we already mentioned these 2 points of exactness, how many channels and which format to use. Other than that, the prompt was exact enough. Let's see if it tried to modularize the code. It did not. So here, one of the problems is that ideally it should have a single modular save function, which would act as our analysis function, and we would call this function for saving both a CSV file and an NumPy binary file. Here it didn't try to do that. It just repeated the chunks of code. It's kind of all right in this specific case because the chunks are so small, but again, not super efficient in terms of if we want to change something or if we want to add another file format to save in, then we would have to copy paste and increase the size of the code. Not super flexible. So the AI unfortunately didn't make it modular. So in real case scenarios, we would go back and ask it to make it as modular as possible, but then potentially making save as its own function. And one way actually to spot this is code repetition. So you can see here that this chunk and this chunk, they are essentially very, very similar. Line 1 and line 3 in both are almost identical. And then the middle line, they're very, very similar. So this is one thing to look out for. If in your generated code you see lines, you see chunks of code that are very similar to each other, that's a very clear sign that something can be optimized and modularized, meaning each such chunk can be turned into a module, and you can call this module to get the results of that chunk. And so you can instruct AI to explicitly do that. And the same thing here for loading. All right, so let's move on to the next notebook. If you have any questions, please feel free to paste them in the chat. We're going to skip notebook 3 because Jay covers it and Shri, they both cover it in their respective rooms. We're going to move to notebook 4, cleaning and processing research signals. Okay, so once again, for those who just joined, when we open Colab notebooks from a public source, they're typically saved on that source's server, not in your Google Drive, which means that if you try to modify something, these changes will not be saved. So you need to ensure that you have your notebook saved in your drive or you download it after making these changes. You can check it by looking here. So here it says that the notebook is stored in GitHub, so on our server. And if I make changes, they will not be saved. So to save the changes after we make them, we need to press File, Download YPYNB, and it'll physically save the notebook to your local machine. Or we can click Save a Copy in Drive. It'll create a copy. And now you can see that this pictogram changed to Google Drive, and it says notebook stored in Google Drive. So now we can edit it, and the changes will be saved in our drive. Okay, let's connect to the environment, and let's go over cleaning and processing research signals. This notebook is all about step 2, analysis. Okay, so filtering a noisy brain signal. We are acting as a signal processing instructor explaining brain signal cleaning. So we want a Python script using SciPy and Matplotlib, again, Python libraries. that demonstrates how to clean a noisy brain recording. It should generate 5 seconds of a simulated brain signal, 500 measurements per second, and it should combine a realistic 10 hertz brain rhythm, electrical interference at 60 hertz, and a sudden large spike representing eye movement or muscle movements. Then it should explain how the Nyquist rule determines what sampling rate is needed to accurately capture the signal. Then it should apply a digital bandpass filter to isolate the 10 hertz brain signal and remove the 60 hertz noise. It should add a simple threshold detector that removes the movement artifacts. And then it should display plots um, and explain, well, what happened. So this pipeline encompasses all 4 steps of our paradigm: data acquisition, number 1, data analysis, number 2, 3, and 4, data visualization, the first sentence in number 5, and data reporting, the second sentence in number 5. So here we are writing the whole pipeline containing all 4 steps. Let us do that, and let's see if it does this, because this is a fairly challenging prompt, a lot going on here, so we might need to regenerate something. Let me reload the window because it's getting laggy. Okay, while it's generating this, you can see that it used the libraries we asked it to use, which is good. And then, well, it generated this huge chunk. As we discussed before, we don't like these chunks. But for now, since we really want to understand what's going on inside the chunk, let's go with it. But for the final pipeline, when we understand it, we would ask it to generate a shorter version of the same thing. One 125 lines, not too good. And as you can see, it didn't try to make it modular. It didn't use any functions. It kind of created artificial modules by separating, um, well, logical modules into chunks of code between these commented lines. Not a really good solution, because again, we cannot reuse some of this functionality. If we change something, we'll have to go back and change the related things down the line. But let's go with it for now. Let's see if it runs at all. It does. Okay. So it generated the plot we asked it to, cleaning a simulated 10 hertz brain recording. So you can see here the raw recording. It has the 10 hertz signal. It has some noise, and it has a movement spike. It bandpass filtered it. It removed the 60 hertz noise. It removed the spike based on thresholding, and it got the clean signal. Now let's go over the modules it generated and see what happened. So the data simulation part is very similar to what we did before. It just used our requirements to generate the composite signal. So it generated the 10 hertz rhythm, it generated the 60 hertz noise, it generated the random noise component, and then it just summed all 3. So it followed our instructions exactly. Well, up to a point. The caveat here is again that we didn't specify, the exact amplitude and phase parameters for generating these signals. So it assumed these parameters here for the amplitude and phase. But again, it's up to us. If we want some exact amplitude and phase parameters, we go back and we instruct it to generate that specifically. Let's see if it accounted for reproducibility. In this case, it did. Despite the fact that we restored it the prompt window. Here it fixed the random seed, so the results should be reproducible. Um, but we should keep it in mind, and we should check for it. If the reproducibility line is missing, then we need to instruct it to add it. It also added some blink at a specific time point. And if we wanted to, we would need to specify where exactly to add it. Okay, then it explained, we asked to explain how Nyquist frequency works and how bandpass filtering works. It did it and left the comments. It also explained how we would detect uh, blink and muscle artifacts using thresholding. And then it generated code for plotting the results. And as you can see, especially in this filtering part, as you can see, it chose the parameters on its own volition, which is, again, fine, because we didn't specifically instruct it to use specific filters. But the important part is that it provided the template for changing these parameters or knobs. And if we wanted to, we can go back and instruct it to use specific parameters. For example, we can ask it to use the fifth order filter instead of the fourth order as it used here. Or we can ask it specific thresholding for a specific thresholding strategy instead of just this absolute value comparison strategy, and so on. So here we left a lot of the choices to the AI. It came up with some of these choices. If we reprompt it, it will probably generate different choices unless we specify exactly what we want. But the overall template works. This is the most important part. And I want to emphasize this step 2 here because especially in standard textbook-like processing, whether it's statistical processing or digital signal processing or some other clearly established methods, AI can be very good at explaining what's going on. So if you are encountering some new processing area that you're not familiar with, I would highly encourage you to ask AI to generate, say, even a notebook in which it explains this concept, and then it provides some activities like this one with the generated codes, and you can play around that concept that you are exploring, and this will really help you understand what's going on. It I'm saying it from the personal experience. Previously, when you work with textbooks or even courses, it sometimes it's really hard to understand theoretical concepts separately from their implementation. And the AI can generate notebooks like this easily, and you can really see what's going on, and it'll explain step by step what's going on. And so it really enhances the learning process. Right, next activity, visualizing how signals change over time. This is a shorter one. So we are acting as a data visualization instructor. We want a Python script that shows how to create a time frequency plot, a spectrogram of a brain signal. So we generate a signal that shifts from a slow rhythm, 8 hertz, to a fast rhythm, 25 hertz. Then we compute a spectrogram to show how the frequency content changes over time. And then we plot the spectrogram. Once again, let's identify our pipeline stages: data acquisition, data analysis, computing the spectrogram, and then data visualization. And then the plain language explanation is data reporting. Spectrogram is a, well, pretty standard analysis tool, so the AI should not have problems with that. Let's see how it does this. Okay, so here it generated a huge chunk of code. And well, from experience, we can know that spectrogram is more of a standard tool. So it does not validate the size of this code chunk. So we can ask right away to generate a shorter version. This is much better. It's very easy to look over and understand what's going on. All right, so we generate the result, the code works, great. Let's see what's going on here. So we simulate the brain signal, we add a small noise. The brain signal contains two sinusoids. One is at 8 hertz, another one is at 25 hertz. Um, and then we calculate the spectrogram and then we plot the spectrogram. So all of our, and then we, well, yes, so it didn't actually add the fourth step. So we'll go back and reprompt it in just a second. So here it only did the first three steps. Maybe it did it in the longer version. We can go back and check. But the first three steps at least are here, and it works. So for the first 2 seconds, you can see an increase in the 8 hertz band. For the remainder of the simulation, you can see the increase in the 25 hertz band. So the pipeline works. Let us briefly address the exactness. We specified the parameters for the frequency, but not for the phase and the amplitude. So it just picked whatever it wanted to. And well, if we are just to specify these parameters, we can simulate the exact waves we want. It fixed the random seed, so it's reproducible, which is good. So it took care of that. Other than that, in terms of exactness, it worked. It is okay, but we are missing our explanation, so we don't have the at plane language comment part. Let's go back to ChatGPT and see if it generated it um, in a longer version. It did. So it provided these text blobs here explaining what's going on, and it generated the interpretation for the spectrogram, but it didn't do that in the shorter version. So we can correct it and ask for the explanation. So we can just say you forgot to add a plain language explanation interpretation for the spectrogram. And well, now we have our interpretation, which we can copy paste back into our code. So let's see what it produced. The bright band near 8 hertz during the first 2 seconds represent the slower resting brain rhythm. After about 2 seconds, the bright band moves to 25 hertz, showing that the brain signal has shifted to a faster active rhythm. Bright colors mean stronger signal activity at that frequency. A pretty on point and short explanation. I like it. So the AI did a really good job here. And one final note about this before we go on break. AI, from the personal experience, AI tends to be really good at finding patterns as long as you're willing to share data with it. I know that it's a very um, critical concept because data privacy in any biology related research is crucial. We obviously cannot just give data, even de-identified data, to the AI for it to use freely because we have no control over what will happen to that data afterwards. However, if you can prompt it to simulate a situation similar to what you're finding in your real data. Say, like this situation where you have two signals at different frequencies and you just want to get some insights on potential interpretation ways or analysis techniques. It is really good at really finding patterns and suggesting um, what analysis direction to take and the possible interpretations for what you're finding. So I would encourage um, this type of usage to get some additional insights on what can be done. All right, so it's 11:30. Um, we have a scheduled break until 12 p.m. and then we will reconnect in this room and we will continue going over the notebooks. We will not be able to cover all the notebooks. The remainder will be the homework, um, but we'll cover as much as we can for the pre-workshop notebooks. So
So, Walt, yeah, before you conclude, yeah, when you're done, let me know because I wanted to say some things.
yes, so I'm actually done. We are going on break
Oh,
until
you're
12
done.
p.m.
Maybe you can turn the video, I mean, the recording off. Let me, yeah. So we've been, I think, please record. Okay, thanks. Go ahead, go ahead.
Yes, so if you're processing this overnight and you have one bad subject with some missing values or zeros, you do not somewhere in the middle, you do not want to lose on the precious hours that could be spent processing other subjects. So this error handling strategy is very important. Now, let's look at the caveats again. So we identified one exactness caveat, unexpected data problems. We specify what we mean by the unexpected data problem a little bit below, zero or none. Um, so here we address this later, but if we are to include other problems or if we are to encounter other problems in the real data, then we either would have to specify or the AI might not generate the correct processing strategy. Because you can see that it hard-coded the missing value processing and the division by zero processing, but it does not know how to react to other problems. So if we encounter other problems, we would have to specify them too to make our prompt a little bit more exact. One good thing that we did here was we specified the processing strategy, try, except, finally. Um, in fact, in Python, that is the default error handling strategy. So if we were to omit that, the AI would probably come up with this strategy anyway. So no exactness problem here. And then we left the login strategy completely to the AI, and it provided the print statements, which might or might not suit our purposes. If it's okay, if we just want to track the the measurements in real time that caused problems, then it is fine. If we are processing a data set with 1,000 subjects, each having 100 trials, then it's probably not the best strategy because it will output something for each trial and it will be impossible to find the exact errors. So um, we would probably need to use a file or report trial IDs or something like that and reprompt AI with this strategy. Here we left it up to the AI and it did it like this. Okay, so this concludes the strategies on signal processing. And let us move on to notebook number 5, finding patterns in brain and behavioral data. We already talked about that a little bit, that AI is very good at detecting patterns and giving insights on interpretation. And the trade-off, of course, is data privacy, that we cannot just give de-identified data um, I mean, we cannot give, we obviously cannot give data containing identifiers, but often we cannot give even de-identified data because we might not have control over what happens with the data. So we need to um, resort to generating similar cases and prompting AI about these similar cases for it to provide us with insights. So let us look at this notebook. Finding patterns in brain and behavioral data. This notebook combines the steps that we learned before. So data acquisition, data analysis, data visualization, and data reporting, and applies them as the standalone pipelines. So here we really have a chance to work with full-on pipelines in more detail. So the first pipeline is on separating signals from individual neurons. We are to write a Python script that demonstrates how to separate mixed electrical recordings into signals from individual neurons. So we are to generate a simulated data set from 1,000 with 1,000 electrical events captured near 3 distinct neurons. Then we are to use a dimensionality reduction method. Here we instructed specifically to use PCA, principal component analysis, to find the distinctive features of each spike. Then we are to apply a clustering algorithm to group the spikes into 3 clusters. And then we are to plot the results as in a scatter plot. And then we have to leave comments explaining what's going on in our analysis. So we have all 4 steps: data acquisition, data processing, which covers steps 2 and 3, data visualization, which captures step 4, the first sentence, and data reporting, which captures the last sentence of step 4. Okay, let's go ahead and do this. Let me restart ChatGPT again to ensure best performance. Okay, it generated the code. As you can see, the code is again extremely long, but it's very well explained. So let me go ahead and ask it for a shorter version of the same code. This is better. It's shorter. Let's quickly go over what it did. So it generated 3 different neuron spike shapes using the exponential functions. And we can already see the caveat that the exactness caveat that we specify that each neuron should have a slightly different shaped electrical spike mixed together with background noise. We don't specify the exact parameters. So the AI came up with some numbers. They might or might not work. So we'll have to either check if this is what we want or reprompt it with exact parameters. Then we generate 1,000 spikes with noise. So for each template spike, we add some random noise. Then we perform the PCA projection. And if we are not sure at this step what PCA is or how it works with this data, we can go back to the prompter and ask it to clearly explain what PCA does and maybe construct some interpretable examples, maybe inside the same notebook, uh, so that we are fully clear as to what's going on during the PCA step. Then we perform the k-means clustering. If we're not sure what k-means is, we can go back to AI and it'll explain what happens here. And we plot the clusters and average spike shapes. Let's see if the code works. It does. So let us try to interpret what happens here. So it generated this three um, um, wavelet type lengths as templates, and then it added random noise to each wave. And these are the average patterns of each wave. And then it constructed the PCA projection on the data points, the noisy data points, and clustered it. And as you can see here, since probably the noise wasn't too much and the shapes were distinct enough, it separated the clusters pretty well, at least visually. So the AI did a very good job of generating this more of an educational example, because here we can clearly see that, okay, if average spike shapes of our neurons look like this, um, then the they can be separated in the PCA space. Let us now go back to the exactness problems. So we already mentioned that we don't specify the exact spike shapes. So the AI just generated some numbers. It worked in this case, but if it chose if it were to choose some different numbers, it might not have worked. Let's see, we specify which dimensionality reduction method to use and which clustering method to use, which is good. It might be exactly what we want. If we were to drop these methods, then it would be able to choose its own dimensionality reduction and clustering algorithms, and might have gotten different results. And then in terms of reporting, as you can see, again, since we went with the shorter version, it did not include this plain language comments, so it skipped the final step. I'm pretty sure that, yes, it was in the longer version, but it dropped these comments from the shorter version. So as we did in Notebook 4, we could either reprompt it to generate explanation, or we could use this blob from the longer version. One final step to take note of is that here, again, it fixed the random seed for reproducibility, which is important because we generate random noise. So this experiment will be reproducible. So this is going to do a good job with that. Moving on to activity A2, predicting behavioral intentions. So we are to write a Python script that demonstrates how a computer can learn to predict what a participant was trying to do based on their brain signal patterns. We simulate a data set with 500 recorded trials, each describing 10 signal features. For example, power in different frequency bands. And each trial has a label, move left or move right. The typical situation for example, EEG, IEG, condition-like data sets. The labels can be correct and correct trials. They can be different movement directions or similar. Here we split the data into training set and separate testing set. We train a classifier to learn the relationship between signal features and intended actions using training data. And then we evaluate the classifier on the testing data and display its accuracy and confusion matrix. And we, again, use plain language comments to explain what's going on in our code and analysis. 4 steps: data acquisition, number 1, data analysis, number 2 and 3, data visualization, the first sentence in number 4, data reporting, the second sentence in number 4. All right. The chunk is generated, and here let's let's go back to one other concept that we talked about previously, modularity. Once again, you can see that in this example, And in the previous example, the AI did a pretty bad job in trying to modularize the code. We don't see any Python functions. We only see a script-like structure where it just performs steps one after another. It is all right. It might be all right in these particular cases because our scripts are fairly short, but ideally we would want to see modularized pipelines so that if we are, say, to change the model or the train test split strategy or result visualization technique, then we could do it easily by just swapping a function. Here, if we change something along the way, we would need to go down and change other things dependent on it, not very flexible. But it is what it is. So let us go with what we have here. Let's see if it works first. It works. Now let's go back and see what actually happened. So again, it fixed the random seed for reproducibility. This is great. Generated 500 brain signal trials with 10 features and assigned random labels such as move left and move right. Um, then it actually added a deterministic shift to ensure that the signals are separable, which is an interesting artifact to see. Let us see if um, it is interesting because we did not ask it to specifically do it. We did not ask it to use the shift. The shift will ensure that um, the signals will be separable between between the conditions, which is, I mean, this is an interesting move by the AI. Um, and that's why it's important to go over what it generates and validate if the resulting strategy makes sense or not. So here it well simplified the problem a little bit. Then we have our train test split separation. It trains a nonlinear random forest classifier on the train data. If we are unsure what the random forest classifier is, we can go back and ask the AI to fully explain what it's doing. And then we train on the test train data and predict on the test data, report accuracy, and report the confusion matrix shown here. So based on the confusion matrix and on the overall accuracy, the AI performed, the model performed very well. As you can see, we're able to achieve 97% test accuracy. But again, this is a little bit um, of an instance of cheating because we are separating the signals to be um, well, to be separable, and that's what we can see in the confusion matrix. Now, in terms of the caveats, this prompt is actually a very good example of what a prompt should look like, what a well-specified prompt should look like, because we specify the number of trials, the number of features, um, what each feature should represent. We specify the conditions that we're interested in. We specify the train test split percentages exactly. We specify which models to use. We specify how to train the data, and we specify what to report. So this is a very well specified prompt, and I think that such prompts are uh, what we need to aim for. The only issue with the output that I can see is the lack of modularity, but with some continuous reprompting, this can be addressed as well. All right, let's go ahead and move on to activity B1, which focuses on step 4, documenting your software environment. We need to write a script that demonstrates how to document the software environment of a research workflow so that a collaborator could reproduce the exact same analysis. An extremely important and extremely valid problem because nowadays it's a common requirement that the codes and analysis need to be published together with the results. And um, future researchers that want to replicate the results would greatly appreciate it if the codes are well documented and if the analyses are reproducible. So relying on AI to do that might be a good approach here because as we saw before, it very often it becomes even over eager in trying to explain what it's doing, and it produces this long chunks of comments. So using AI for documentation and reproducibility might be a good idea. Let's see. So where to check for a specific configuration setting stored outside the script in some variable. If it's not found, where to print a warning and switch to some default modes. We have to print the exact version numbers of key software libraries the workflow depends on, and save this information as a software environment record. This is a very important step because the libraries continuously get updated. Some functions get deprecated, some functions are added. So the code that works with one combination of libraries and packages might not work with another combination. So it is very important to provide the exact package versions so that somebody can reproduce using the exact package versions. Then we are to demonstrate how to handle a sensitive access key, such as a password, by storing it as a system variable rather than writing it directly in the code, and show what would happen if we were to accidentally print it to the screen. And then we have to explain what's going on. Once again, this is a pipeline, so we can identify our paradigm steps. So in this case, we have this case is interesting because we are skipping the data generation step and we are starting with the data analysis step because we assume that the data were already generated and the analysis and some of the analysis were already done. Or I would say we are proceeding directly to step 4 actually. So we're skipping acquisition, visualization, analysis. We are right at documentation. So we are right. We're assuming that everything else was already done, and we are just recording the library versions and ensuring that the data are stored in a secure way. So let us prompt AI with this configuration. Generated a longer chunk, but in this case, it might be beneficial because we are asking it to do a lot of things. So let's use the code that it generated. Let's run it, and let's see what's going on. So first, it reads a configuration setting from the environment. The variable name is research mode, and if it's not specified, it reverts back to the default mode. And as you can see, the research mode is not specified, so it reverted back to the test mode. And this is a nice way to branch your pipelines in a sense that you can have some external variables. We talked about them in terms of them being knobs, that if one knob is set, you do this. If another knob is set, you do something else. So this is essentially what's going on here. So if, say, we set one of the knobs to the testing mode, then the pipeline will output one collection of data and results. And if the knob is set to some other value, to some other mode, then a different collection of results will be saved. Then we record the exact software versions, and they are reported as a file. They are saved in a file called softwareenvironment.txt. And here it reads and prints out what was saved. So these are the exact versions of the libraries and packages that we're using. And it notifies us that these were saved. And then it outputs this educational chunk that tries to read a sensitive access key and well, it demonstrates that we should not print the access key because typically it's a sensitive, it contains sensitive information, and instead we should store it somewhere in some secure location, but we should not print it to the screen. So overall, what we can learn from this exercise is that it's important to document the library versions for constructing reproducible pipelines. And especially if there are multiple users, it might be a good idea to set up some branching logic based on some knobs. And if the knobs can represent modes. If one mode is set, one collection can be saved. If another mode is set, then another collection of results can be saved. And one other thing, again, this code style is more script-like, not modular. So ideally, we would like to see more functions here instead of just following a plain script. All right, we are done with Colab number 5. Let's now go to Colab number 6. Putting it all together, your complete research workflow. Now we need to try to unify everything that we have learned so far, the strategies that we used, the caveats that we learned to identify. So before starting that, let us just sum it all up. When using the AI, we need to be very careful about how we specify prompts and how much freeway we give to the AI. Because if we specify some steps ambiguously, the AI will interpret it in its own way, and reprompting it might produce different outputs. We also need to validate what the AI is doing, meaning what exact code steps it generates, because sometimes it might try to make you feel better and include steps that you did not want, but that produce better results. We saw that in the signal separation example. If you, one good strategy here would be to go chunk by chunk and explain and prompt the AI to explain why it included that particular code piece and what was the reason for that. Another strategy is modularization. It is better to try to use independent to construct your pipeline in independent stages so that one stage is only connected to the other one, but they're not dependent to each other explicitly, in a sense that you don't have one large black box where you have everything, but you have clear steps like obtaining the data, analyzing the data, visualizing the data, reporting the data. This is extremely important for both debugging and flexibility. And it's better to work with AI stage by stage. So first work on the first stage. Then once it's done, you can reprompt it to say, okay, great. Now let's generate the second stage. Okay, great. Now let's generate the third stage, and so on. And one other caveat that we saw was that sometimes AI does not include reproducibility guardrails. It does not fix random seeds. So it might be a good idea to always go and just check that the seeds are set so that you're fully sure that whatever it generated is fully reproducible. With all that, let us go ahead and look at Colab number 6. So activity A1, the complete integrated research workflow. All right. We are a lead neuroscience workflow designer, and we want to build a complete end-to-end analysis pipeline. Sounds exciting. We are to write a Python script that connects 4 completely independent, clearly separated stages into one working workflow. Note that this is a really great sentence because it instructs AI specifically to work in this um, modularized paradigm, which is exactly what we want because of reasons we discussed. So stage 1, obtaining the data. We are to generate a simulated 64 channel brain recording with some background noise and movement artifacts. During stage 2, we are to clean it, to clean the generated data and threshold it and to remove the artifacts. Then we are to extract key summary features. Then we are to visualize the results, and then we are to document the research. Let us do this, and let's see what it comes up with. Okay, so you can see that it generated something really, really, really long, and this is not what we want. As we saw before, typically we want something short, and this is not it. We want something short because then it's easier to debug it and see the big picture right at the same time. So let's reprompt it right away and say generate a shorter version runnable in a Google Colabs cell. Okay, still long, but much shorter than it used to be, which is great. So let's try using this version. So it made an attempt at modularizing it. As you can see, again, it tried doing it via these comment sections, not via functions, which is not the best strategy, but we'll go with it. So it generated the data with the knobs it specified. So it assumed some sampling frequency, number of channels, duration. It fixed the random seed for reproducibility, which is great. It generated the data. Then it tries to process the data, and it reports if it was successful. It extracts mean, amplitude, mean standard deviation, and some additional statistics. Then it visualizes the results, and then it documents the results. Let's see what it actually visualizes and what it actually documents. Okay, great. So it reports its progress. It says when it outputs when the stages are complete. So So stage one was done, stage two was done. It removed some artifacts. So you can see here the raw signal, and you can see here the clean signal. Once again, it uses the thresholding strategy that we looked at before. Then it visualizes the results, and it has the workflow log.json saved. So in Colab, when something saves files, they're saved inside the Colab environment. And you can look at the saved files by clicking this files icon here. And so here is the file it's saved. It's called workflow log.json. And if we are to look at it, you can see that it documented number of channels, sampling rate, duration in seconds. It documented the threshold it used for artifact rejection, and some additional parameters. So the conclusion from this is that it did a pretty good job given its constraints. It generated a runnable code. It documented it well. It produced some plots. It didn't write a human interpretable conclusions, but we can prompt it to interpret the results. In terms of the caveats, it didn't try to really modularize it, only in this synthetic modularization with comments. And then in terms of the prompt specification, we again used some general terms here, such as realistic background noise, some sudden movement artifacts. We did not specify the exact nature of the noise or artifacts. So it was up to the AI to decide, and it came up with something that worked. But if we're not happy with that, we can go back and regenerate that